a lot of work on machine learning and healthcare. And so we're very happy to hear what she has to say today. Please take it away.
Hello, everyone. Super excited to be here. This is my first time at Simon, so learning a lot from the talks, and I appreciate that I am the last thing between you and lunch. So let's talk about something really fun and interesting and hopefully keeping you engaged the whole time. As mentioned, I have a million joint appointments, including across Berkeley and UCSF. So if you have any questions about any of them, just let me know. All right. But today, as has been a theme through the morning and even in the talk right preceding mine from the lovely talk from Robin, we are living in a day and an age where the data sets are starting to matter a lot more than they used to before. And in particular, I have been really struck by how the data sets, as they get bigger and bigger, have started to come from many different sources. So even something like the PILE data set is an amalgamation of a lot of sub data sets that you sort of conglomerate together and then use for example, pre-training on a large language model. Even for specialized tasks like things like code generation, code synthesis, you want to be able to combine many different programming languages. And the assumption there is, of course, the more programming languages that you can add to your corpus, the better the performance might be later on. My main focus of research interest is in healthcare. And when we think about healthcare, we start to think about different modalities as well. So my research spans things like electronic medical records, hence the UCSF affiliation, as well as wearable data, molecular data, medical imaging data, et cetera, which becomes collected into data sets that are collected across many different sources. This is a theme that'll come up over and over again. All three of these data sets have yielded, I would say, thousands of publications on each of them. And notably, they are collected from many different geographic locations, many different recruitment centers, many different years of collection that then get sort of thrown all together in hopes of advancing machine learning progress in, for example, healthcare. So when we boil it down here on the x-axis, we have data set size. The implication is that we hope it will improve performance. And if we sort of use our imagination, let's think about what this line, what this curve might look like. So curve is probably biasing you a little bit, but I think many of us might expect that the performance as defined as accuracy, fairness, robustness, I know many of the people in this room have papers, including myself, on things like this. It will increase rapidly for a little bit, and then it'll start to hit diminishing marginal returns and start to plateau off. And in fact, this is the problem that, and in fact, the question then becomes, well, where is the limit? And as this data set size increases, particularly over many different sources, how should we start to think about this curve? This is a project that two PhD students, the lovely Judy Chen at Stanford and Deb Raji here at UC Berkeley, and I worked on, particularly how to balance what we call data accumulation, or sort of more is better data, with the very real distribution shift that may occur as you start to incorporate many different sources. So let's talk about a specific focused example. So let's say you are UCSF, we're in the Bay Area, you're at UCSF, you run the machine learning division, and you would like to make an algorithm that works very well on UCSF, future UCSF patients. As you add more and more training data to the model, you might start to see this characteristic curve that goes up and starts to maybe plateau, but UCSF does not have infinite patients. In fact, there are a limited number of individuals who have come through. UCSF actually, fun fact, digitized its records in 1980. So there are patients going way back, but eventually we will run out of hospital data from what we'll call the anchor hospital, UCSF. Fortunately, through collaborations or meeting folks at conferences like this wonderful Simon's workshop, you might have a lot of friends at different hospitals, here indicated by their de-identified anonymized hospital number. And you might be able to persuade them, get our lawyers to talk to each other, have the data standardization work, et cetera, yada, yada, yada. But the idea is that maybe if you could borrow some data from them, you could improve your performance on your, let's call it, anchor hospital again. And in fact, what we found is when we explored the different data, potential additional hospital data sources that we could add to our model, the resulting AUC could go up as indicated in red, but it could also go down. And that was quite a surprising result for us to find. And in fact, just highlighting two sort of extreme examples across the spectrum, it did not matter that this one hospital had a lot more data to be able to add, but in fact, sort of a higher quality by some metric hospital was able to increase the AUC even for being a smaller data set to potentially add. And so this tension between which data sources, yes?
Values on what data set?
The test AUC is evaluated on the anchor hospital. So that's a great question. So remember that you are the UCSF machine learning research lead, and you would like to improve your performance on your own hospital. And so we'll go into a second why this might be different from domain adaptation as defined by many other folks in this workshop as well. So from the perspective of that one hospital, you could add other data sources, but you might in fact find that you would be wasting your efforts, and then in fact a smaller data set might be better. Question in the back.
Is there also measure of like how the covariates compare between the
Yeah, so the question was about how the covariates might compare across different hospitals. If you're asking about the type of covariates, we're assuming that you are able to measure the same covariates across all the different hospitals, which would allow for a comparison like this. In practice, you might find that some hospitals don't take the blood tests in the same way, but let's say we're abstracting that away for right now.
In the sense, I'm asking a question in terms of some hospitals are similar, have similar population to.
Yes, so exactly. So the comment for those who can't hear is that some hospitals might have similar populations, and that might be playing in. Exactly. Stay tuned in 10 minutes, and we'll talk about more about that. Anyway, so that is how we define. Oh, one more question.
Yeah. So how should I think about those points or lines? I mean, did they refer to specific? Like if you're treating all the data the same, or because I mean it's this isn't. I mean these are just upper bounds using some method. I'm curious if you're thinking of a particular method, or I mean,
this is trained on an LSTM off of a 200 hospital data set.
But how are you using the additional data?
How are we using the additional data? So you would combine the data from this hospital with all of the data from the original hospital, and you train a model on the combined data set. Yeah, so you can treat them the same. Although in fact, the slightly more than 4,000 compared to the 2,000 original would mean that the new data set would be primarily new hospital as opposed to the original data set. These dotted lines, as you can imagine, are actually not real because we only compare just using the full data from each hospital. Does that answer your question?
Yeah, I assume later on you'll talk about other methods of combining.
Yes, exactly. All right, but the general idea is that how are we going to combine these data? Would adding more data be helpful? How should we think about this in a rigorous fashion? This is not new. This is actually seen in other cases, not just healthcare. For example, our friends at Google thought about this in the case of translation. So in 2019 in NACL, they published a paper, massively multilingual neural machine translation. And the question here is, should we build one big giant language corpus and train a translation model over that? And how would that compare to let's say, pairwise methods? So instead of English and French, English and Swedish, English and Chinese, or Mandarin, should you just have sort of a giant thing and then learn all of the common representation and be able to overcome that challenge? And what they found, so they looked at if it would be better for pairwise methods versus worse than pairwise methods. And they also were interested in how this would compare for languages with, quote, less available training data, we call under-resourced languages, things like Sanskrit, for example. And they found two findings. One is this blue line, which is that if you had one large multilingual corpus, you would systematically lower performance. So this is notably lower than the neutral line for all languages compared to a pairwise method. So having one big corpus, not so good for performance. And in fact, if you wanted to overweight things, so if you oversampled low resource languages, you could actually start to get performance improvements compared to pairwise methods, but you would not see similar benefits in oversampling for already well-resourced languages, as they call it. Yes. Pairwise methods are a specialized model that goes from English to French, English to Swedish, and you just train on a corpus there compared to a giant corpus of all the languages and learn representation there. In the paper, they propose then clustering the languages and building sort of like cluster-specific models that would have a sort of a more related corpus and building from there. Yes?
I'm a little surprised by this, days. I'm actually working
Oh.
for Google.
Fun. Okay.
And
Do you guys still do this?
I think what surprises me is that there is a result that says exactly the opposite of what you're saying. So I think what's probably what you mean here is that what they're doing here is some like straightforward method, putting all the data together, or is that?
I have talked to other folks at Google, particularly on the translation team, about this.
There are articles that are saying exactly the opposite of this. Like using all of it at the same time would be better. So but it depends on what you do with it.
Yeah.
Yes, I think the way you combine it can be important. I would say the claim here is that throwing it all into one corpus and just training a representation, calling it a day, is not helpful. And I think we could probably agree on that.
That should not be too surprising, as in the previous results that you.
Yes. Yes. Anyone else work at Google who can share? The folks that we have talked to, I guess this is being recorded and streamed, who knows, have said that Google is now using Gemini for translation potentially. And so all of this is perhaps not relevant anymore either. But the overall concept is there. Yes.
Well, that again goes against, because Gemini is one model
Yes.
of the languages. So.
But there's like a pre-training, there's like more nuance than having one large multilingual corpus. Maybe? All right, let's chat at lunch.
I mean, I think that all the issues here, it really depends. These are all like upper bounds in performance, right? It really depends what you do. And so this is, I think, why we're a bit uncomfortable.
You mean lower bound?
Lower bound, right?
Lower bound in performance, yeah, upper bound on
Yes.
yeah, sorry, lower bound.
Lower bound. All right, other comments or questions? All right, so the workshop is about domain adaptation ostensibly. I just want to sort of make a very crystal clear point here, which is that our goal is not to perform very well in other domains. We're sort of really focused on our own target and source domain. And the question is what kind of data we should be bringing in to be able to help our setting. So I want to make that clear, although of course domain adaptation is a very valuable question that many folks in this room are working on. So, I guess the domain, the source and the target are the same in this setting. So you would bring in other data. There are many different domain adaptation type of algorithms that would work, but ultimately it becomes a slightly different formulation because we're not trying to take a model from a source domain and move it to a target domain. In fact, we're just staying in one land. Is that your point? Great. So specifically, we're interested in formalizing and weighing a cost and benefit of adding more data. So let's try to formalize this. So let's say you have some data, X and Y, and data points drawn from some data distribution. That's actually not the same data distribution. That data distribution is composed of many different sources. Let's call them M data sources of many different sizes, as denoted by the M different sources. And in fact, that becomes your training data. And the question becomes, how would we relate the training data that we have and maybe we want to learn on to the performance that we'd want to pull off of some sort of test data set? Our test data set here being focused on one source or one domain, one hospital, one language, for example. One way to think about that would be to do something pretty straightforward. The dumbest thing we could think of would be something like, what is the AUC, some performance metric that we've chosen, of adding this last data source compared to without adding that last data source? Could we imagine the marginal benefit of an additional data source, particularly if that data source is going to cost a lot of money to standardize, to make sure all the covariates are observed? And one relaxation in order to start studying this in the first place would be to just think about two data sources. Can we compare what happens before and after adding the data source, even if the H0 source here would be less than the H0 combined with the H1? So in the original data set we looked at was this 208 hospital intensive care unit data set that's collected by Philips and MIT. And what we found looking at the 12 largest hospitals on a prediction task where we're trying to predict the 24-hour mortality. So you have 24 hours of data from each patient, the first 24 hours, and you're trying to predict if they will die in the hospital, if there will be a fatality as a result of after the first 24 hours. And okay, on the x-axis here, we have the test hospital, which would be the anchor hospital. And the y-axis, we would have the additional data set that you're adding to that original. And the value of each cell here is the difference than if you just didn't include that extra data instead. And so, for example, here we have a red square. The color rendering did not turn out super well. And the red square here means that for hospital 167, if you add that data to hospital 199, then it will actually drop the performance for hospital 199 compared to if it didn't use 167 at all. If you just stuck with 199 data, even though it's less, you would have done better. Adding it made it worse. And so with that intuition, you can look across the whole 12 by 12 grid here and see that there are some blue, which means that adding that hospital did improve. And there's some red, which means that sometimes when you add a hospital, it does not improve. So can we start to characterize when you would be able to predict that, when you would be able to know that, and what would describe that kind of phenomenon? One of the things that we found is that this AUC change from adding hospitals is correlated pretty strongly. We have a e to the -9 p-value with the change of outer distribution AUC change. So this is just predicting, given two data sets, can you predict which one is in which distribution? And in fact, there's sort of a straight line when you think of all pairs of hospitals that allows us to make that claim. So we then relate this to the divergence between data sets. So instead of looking at a specific model, things like an LSTM AUC, could we start to reason about the data sets that we're looking at specifically and discover whether or not this divergence could help us choose which data sets to add or not? So when we look at a toy toy example, here we see that there's a high quality data source 1 and a low quality source 2. And we'd like to figure out how would we relate this divergence of a trained data and a test data, which is test is now here in gray. If the training data size is just smaller than the source 1, we would just use all of source 1, and then the divergence is described as so. And then if it's not, we can it starts to get a little fancier. So if we assume that divergence is composed linearly, we could just do a linear combination, easy peasy. But if it doesn't, and this sort of becomes the part of the paper that's a little bit more theoretical, could we start to upper bound what the additional data divergence would be for the case source? And this relates to both the data that's collected from source K, as well as the existing data in the test set as well. So here we're assuming that we would have access to the test set, and we'd be able to perhaps take a divergence between the contemplated new source and in the test source as well to figure out, would this in fact help our model or not? So this is related to a whole world of data distances, divergences, discrepancies. That's not the focus of today's talk, but I'm happy to chat more. And certainly in some of our future work, we're starting to dig into this as well. But let's keep things practical for now. So you are a person who is building a model and you would like to be able to figure out which data sources to add. Strategy 1 was you could try all the combinations. We did that for one hospital. You already have one hospital and you want to figure out if you want to add another hospital. As you might imagine, if you want the best 3 hospitals from 10 different options, all of a sudden you're looking at an exponential combination. So it's not quite feasible. Some would call it intractable. Another idea, and this came from the back of the room, is that when we talk to practitioners, they said, oh, we don't really care about how it helps the model. Well, we care about how it helps the model, but we don't have the tools to try all the different combinations. We would find the hospital that is the closest to us in race distribution or gender distribution or age distribution. That came up a lot. And in fact, we would just use the nearest one, maybe a vector formulation of the distribution and do some sort of distance from that. And we would choose the best hospitals that way. And then the last thing, motivated by all the stuff I just said, is we started exploring divergence-based metrics. We looked at first the KL divergence between the data set, one data set and another data set. And we included both the X components. So in this case, it would be the ICU measurements. And then we also considered concatenating the outcomes in the world where you want to start to measure the relationship between the X and the Y specifically. KL divergence is quite tricky to compute numerically. It's a little bit unstable. And so then we came up with a score function, which is simply the numerator of the KL divergence. And this is a probability that a given point would be in the first data set distribution that you're looking at, or the second one, if the idea being that if they are close together, if it's hard to differentiate, then the data sets would be very close together. And if it's easy to differentiate, it would be quite far apart. So 4 different divergence-based metrics that were compared, and we're comparing that to, say, something like hospital level characteristics to understand the source level characteristics. One of the ways to figure out if these metrics even work is to see if they correlate with the AUC drop. So here we went through all of the different pairwise hospital combinations in this data set that we've been looking at, and we found that in fact the AUC drop was correlated with, say, the score XY for the specific setting, and the p-value is quite striking. And so we then compared all of our different metrics, the 4 that I just outlined, as well as the race distribution, sex distribution, et cetera, where we would choose a cosine distance between 2 hospitals and say if they're close together, it would be considered close versus the AUC drop might be further away. And we found, so this is the Y value is on the log scale. Dotted lines are p.05, p equals 0.01. And we found that actually the distribution metrics perform a little bit better, statistically significantly better than any of the hospital-wide characteristics that we chose. The data set that we looked at does not, it anonymizes the hospitals. So you can't say, oh, you know, they're like 10 blocks from each other, but instead we can look at the patient distribution, and we could also look at the region that the hospital was in the country, something like Southwest or Northeast or something like that. So this was promising, but one of the sort of concrete things we wanted to compare was how did this look in practice? And so when we think about this curve, again, we see you add more data from the original hospital, you run out of data, what are you gonna do? If you choose the 3 hospitals that are available based on, say, the score function for XY, which is the highest performing divergence metric we looked at, you can see that the AUC continues to go up and up and up. Even though you're out of your old data, it kind of looks like it sort of continues on. Meanwhile, if you add data from the 3 worst hospitals, you may not have as good performance. And in fact, even if you had stopped here, you'd see that it goes down way far. And one of the baselines that we looked at was adding a mixture of all hospitals. So is there a way that we could look at the full slate of possible options and then weight them by prevalence in the entire multi-corpus and see how that works? And we see that even being a little bit more careful about choosing 3 best hospitals outperforms this dotted green line as a result. So that's one hospital. That was the largest hospital that we looked at. We found that this occurred over and over again, depending on other hospitals that we looked at as well. So here's the 2nd largest hospital in the data set. Again, blue line, 3 best hospitals outperforms orange line, 3 worst hospitals. And then our green line, our mixture is somewhere in the middle. There was a question earlier about different ways to weight the data sets. I forgot who asked. And so I think that that's also in the paper of sort of like, could we do a weighted mixture? Could we in fact use something like the score function in order to put weights on the different hospitals as well? I think you were about to raise your hand. Oh, this is the score XY function. The score X and XY you can see is like pretty similar. The KL divergence, slightly, you know, it's sort of like the lines start to blur a little bit as well. I think I would blame the numerical stability of the KL method that we used. Yes.
Did you try like a 2-stage training? Like first train on the other hospitals and then you train further just on yours? So that
yeah, as I was listening to your talk, I was like, oh, that would be really interesting to think about. We did not for this preliminary paper, but we were sort of an active line of different, I would say, better baselines that we could compare against, or maybe depending on which baseline wins, we'll make that our new method as well. And then sort of a coda that I want to add or make sure that we're sort of looking at. We were looking at the top line accuracy. We wanted to improve the model overall, and we had no regard for how it works for different subpopulations. But in fact, what we found is that the racial disparity was quite an important thing to examine. And so here, there are 6 different racial groups. We define disparity as the difference between the highest performing group and the lowest performing group, and it's a loss, so lower is better. And from the 2 hospitals that I just showed on the previous slide, we see almost contradictory results, which is that adding the 3 best hospitals lowered the disparity in this case. And in fact, adding the 3 best hospitals increased the disparity in this case. And this is maybe not, it's hard for me to really wrap my head around, other than to say we were not trying to optimize for any of it when we chose these hospitals. And therefore, we probably are unsurprised to see that it sort of varies a little bit as I go here. So sort of as a recap, I think I've completely lost track of time, but the high level idea here is that we'd like to be able to benefit from larger data sets. Larger data sets contain many sources. We'd like to be able to figure out what's going on there. We show first steps towards this idea that you could start to reason about the data distributions as a way of composing a data set towards better performance on a fixed anchor setting. And we show that the divergence method outperforms maybe more normative statistics about, oh, this data source is sort of similar based on my intuition, but we can in fact reason about when to add more data. We have a lot of different ongoing projects right now. I think this is sort of energize the lab thinking about, oh, how would we think about fairness if we wanted to pick the hospitals that would best improve fairness while still maintaining accuracy? How would this scale for different modalities? So these were tabular data results that I showed. In a world where we're looking at text, in a world where we're looking at medical imaging, how would we reason about the high dimensional data there? There's some impossibility theorems that we're working with folks at the Simons Institute in. Can we prove that it wouldn't improve or that you're sort of capped in some sort of way? And then lastly, the motivation here is a world where you maybe want to buy someone's data set and add it, or have your lawyers start talking to each other to negotiate a data use agreement. Is there a world where you could do a KL divergence in a privacy preserving way, in which case you could sort of skip some of those steps if in fact that data set will not be helpful to your eventual anchor task? So my lab works on a lot of questions of equity and inclusion in healthcare. So this is sort of just in the data collection part of sort of the things we work on. If you ever have any questions about everything else, please let me know. I always love brainstorming more ideas. But overall, I would say we need a more data-oriented perspective of how to deal with larger and larger data sets. And in particular, this work looked at data divergence methods there. So thank you so much for your attention.
There's time for some questions.
All right, right in the front.
So there was a series of results for precisely the problems that you are talking about, including for the privacy part, actually. I don't know if you're aware of.
Do you have a citation that you can point me to here?
Yes, about like 5 or 6.
Okay, why don't we chat in the break? Fantastic. Folks? Yes.
When you compare the similarity between the data sets, what if you only compare with the ones on which the algorithm fails?
Oh, well, if you compare similarity between data sets, what if you compared only ones for which the data set fails? You would need, or for which the model fails. You would need to know which ones the models are failing on already. So I think part of our motivation is that we didn't want to have to do this like n to the k different training and brute force approach.
The hospital,
the original hospital. So you train the model, and then you're not doing well on these set, and then you want to find new data points that are similar to the ones you're not doing on. That's a great idea. We tried that for just this data set, and it doesn't seem to help, but I imagine there might be a way to say learn a representation or characterize it in a more clever way. We just looked at like these 3 points, how do they map to the other points? Yes.
So I'm a bit confused as how to take this, because as I said before, this is all lower bounds, and in some sense, if we look at like what's the best you can do, the line would never go down. Right? Adding more data could never possibly hurt me, because I could always ignore it. Right? That's one way of using it. That's a baseline way of using it. And so the question is, how can I best use the additional data? And I'm a bit confused by this, like thinking of it as just, does it help me or does it not help me? I mean,
yeah.
Or does it hurt me? Because it never hurts me if I do the right thing.
In a world where you have infinite access to infinite data, yeah, choose whatever subset. In a world where you have to pay for data, in a world where you have to pay for data, in a world where negotiating that takes years of PhD life. I think that
Sure, so you can ask how much does it help, but it should never go down. It never hurts me.
I
mean,
understand.
here you're not measuring money here, you're just measuring accuracy, right?
Yes, but I'm saying that maybe we shouldn't go through all that work to gather that data if it's not going to be, if we're going to just ignore it later. Does that make sense?
Well, that I agree, but the fact that the line goes down means that this lower ground is extremely not tight. The real question to ask is, how do I use this data? Not like just throwing it in there, hurting or helping.
I think we might be disagreeing about the extent to which we want to have access to all the data. Maybe we could chat about that.
Yeah, but I guess one way to see that it can never hurt is simply that you can ignore the bad.
Yes, but if you've so if you want to lay on top of all of the utility function about data acquisition costs,
then that's a different problem.
Right.
Should I have acquired it at all?
Yes.
If it wasn't going to be that
Yes.
useful to me, right?
yes. And so I think reasoning about that is my primary concern.
Yeah, that's-
Yes.
In terms of the distributional understanding between these different sources, do you have a sense of, say, the bluest one versus the reddest one, how different the X distributions are from the black ones versus the Y given X, how much overlap there is between the X distribution?
Yeah, we've looked at sort of like all the representation visualization that you might imagine, you know, your standard t-SNE, or even just seeing how easy it is to classify the two. It's not immediately obvious. It's not like we found a smoking gun of like, oh, these people, no one from this hospital has this one disease, and therefore that's why it's going down. We can see that they are different. We can see that the red ones are more similar and the blue ones are further, but at this point, we don't have a clear explanation of what is going on to be able to describe these variations.
So following up on that, if you just fit the model to the blue one, just to make sure I'm following, and the model just on the black one, and if you just compare their differences, it's actually not that clear how different that is compared to the red one.
So the blue dot is the combination of the data. But if you were to train separate models on both of them, yes, we find that they're further apart. The representations of the two trained models are further apart. Was that your question? Okay. I believe this man had his name. Hi.
Hello, I just wanted to ask, so to assess the divergence measures or the relevance measures that you have, you still need data from that domain, right?
Yeah.
But can we not just use this initial stage? I mean, of course, we might need smaller data to assess that, but is it possible that we just add that data to our data set and see if accuracy going down and maybe not purchase the whole data set?
Yeah, the way that a lot of these data set purchasing things are set up is that you would buy like 1% or 5% or 100%. And then if you assume that the 5% is representative and the KL divergence has these confidence intervals, then you would be confident with a 5% purchase.
But adding that 5% to your data set wouldn't really.
Oh, no. But the idea is that computing the divergence would give you a proxy to be able to guide that. Yes.
So interested in the result you showed where the underrepresented performance goes down when you add the so-called best models. So did you looking at other divergence measures for that, like ones?
Yeah, we've tried, well, we're currently in the trenches right now. We've tried like, oh, does the Black population from this hospital look like the Black population from that hospital? We've tried to do the people that we make errors on look like that population. We've tried a whole slew of them. And to be honest, we haven't figured out anything yet. So as you might imagine, fairness is quite tricky, or rather looking at a subpopulation in order improving the performance on the subpopulation while maintaining the overall accuracy is a thing that, while also selecting for the best data sources, is something that we're working on actively right now.
Quick question about the privacy aspect of what you're mentioning. Because I imagine that mortality within 24 hours is a very critical question for a hospital. And I imagine that anybody here would be very interested in having those numbers for different hospitals. How is it that you're managing to negotiate to have access to this? That's one question. The second one is, how about if you could negotiate without having access to the data, but instead having access to only predictors for each hospital? And I'm mentioning this because there's actually a good solution, good theory for that case, but But that would be a much less demanding, data set preparation.
So your first question, how are we getting access to all this data? This data set is one of the 3 data sets I showed at the very beginning, the health data sets. It's the EICU data set, and it has 208 hospitals in the US, and it was collected spending millions of dollars by MIT and Philips, and now they've open access it to folks who are taking a roughly 5 to 10 hour training to say, I'm not going to post this on the internet. The second question is sort of what kind of access you might have about the data. So if you have access to, say, the predictors, then you might be able to do a lot of understanding about what's going on. So another hospital gives you what they predict for.
No, I mean, black box.
Oh, if you have access to the trained on that hospital. Yes. Would we ever run into that? To be honest, it's unlikely that another hospital would want you to have access to that in the same way.
It doesn't reveal anything privacy.
Yes, it's not privacy leaking of anything. One of the things in working in healthcare is that capitalism comes into play. And so many times the hospital will just deny you not only data access, but any kind of intense discussion with their data science team unless you start signing agreements, unless your lawyers start talking to each other.
Then, apart from that MIT data, if you wanted to negotiate with another hospital, would you be able to get any data of the type that you mentioned?
I did my PhD at MIT, and we spent most of my PhD negotiating with other hospitals. So, surprise. Of the 3 data sets, so these are the 3 largest data sets that are out there. The EICU one is what this whole presentation has been on. The UK Biobank can be yours for the low price of $40,000, 4 or 5 years, and then you have to give it back. And then the All of Us data set is free, but it is a little bit more limited. And you also have to do 10 hours of training, et cetera. So this is sort of state of the art as it goes. But if you're a professor and you're willing to spend a lot of time, you can in fact spend money, startup funds, negotiation, lawyer time, trying to get access to even more data sets as a result.
Okay, so in the interest of lunch, let's call it. Please be back by 2:20. The sessions will start at 2:30 in the afternoon.